Hello everyone. Today we are going to analyze this beam using stiffness matrix method. Before analyzing, let us see the beam one time. In this beam, there are two spans, span AB and span BC. In the span AB, there is a point load 50 kN acting at 2 meter from the point A. In the span BC, there is uniformly distributed load 24 kN per meter acting for the full span. In the point A and in the point C, we are having fixed supports. In the point B, there is a hinged support. Span AB is 5 meter long. Span BC is also 5 meter long. In this beam, we have to calculate 4 moments. In the fixed support, there will be a moment. In the point A, we are having fixed support. So, there is a moment MAB. In the point C also, we are having fixed support. So, there will be a moment that is MCB. In the joints, there will be two moments. We are having only one joint, that is joint B. In the joint B, there are two moments, MBA and MBC. Also, we have to calculate three reactions, RA, RB, and RC. Now, let us calculate the fixed end moments. For calculating the fixed end moments, we have to assume every span as a separate fixed beam. First, let us take the span AB and assume that it is a separate fixed beam. Before calculating the fixed end moments, let us see the formulas. In this table, you can see some of the important fixed end moments for the different type of loadings. In the span AB, there is a point load which is not acting on the center. So, we have to select this condition. The fixed end moment formulas are minus WAB square upon L square and positive WA square B upon L square. In the span BC, we are having UDL for the full span. So, we have to select this condition. The fixed end moment formulas are minus WL square upon 12 and positive WL square upon 12. Now, let us apply the formulas and find out the fixed end moments. In the span AB, we are having a point load. This point load is not acting on the center. In this case, we have to split the span into two parts, A and B. We have already seen the fixed end moment formulas minus WAB square upon L square and positive WA square B upon L square. M of AB will be negative because it is acting in the anticlockwise direction. M of BA will be positive because it is acting in the clockwise direction. Let us apply the values inside the formulas. W is 50, A is 2 and B is 3. After calculations, we are getting M of AB is equal to minus 36 kN meter and M of BA is equal to 24 kN meter. Now let us calculate the fixed end moments in the span BC. In the span BC, we are having UDL acting for the full span. We have already seen the fixed end moment formulas minus WL square upon 12 and positive WL square upon 12. Let us apply the values inside the formulas. W is 24, L is 5. After calculations, we are getting M of BC is equal to minus 50 kN meter and M of CB is equal to 50 kN meter. In the stiffness matrix method, we have to check the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. In the roller support also, there will be slope. In this beam, in the point B, we are having a hinged support. So, the number of supports where slope occurs is equal to 1. In the point B, we are having theta B. So, in this analysis, there is only one unknown, that is theta B. If we calculate this unknown, we can easily find the final moments. Now, let us make the fully restrained structure. In the fully restrained structure, there will be no slope. We know that only in the fixed support there will be no slope. So we have to remove the hinged support from the point B and replace with the fixed support. Right now in this beam there will be no slope because all the supports are fixed. That is why it is called the fully restrained structure. We have made the fully restrained structure. Now let us make the coordinates diagram. In this analysis, we are having only one coordinate because there is only one support where slope occurs, that is the point B. Here we have to make the coordinate. The coordinate should be made in the clockwise direction. You can see that I have made the coordinate in the clockwise direction. Now let's see the formula to calculate the slope value. System displacement delta matrix is equal to K matrix inverse into P matrix minus PL matrix, where PL matrix is equal to moments developed in the coordinates due to the given load. P matrix is the final forces acting in the coordinate direction. K matrix is the stiffness matrix. In this formula, first let us find PL matrix. We know that PL matrix is the moments developed in the coordinates due to the given load. In this analysis, we are having only one coordinate, that is in the point B. In the point B, we have calculated two fixed end moments. They are M of BA and M of BC. We have to add both of them. After adding, we are getting minus 26. For PL matrix, we are having only one value because we are having only one coordinate. In this formula, now let us find P matrix. We know that P matrix is the final forces acting in the coordinate direction. If in the beam there is overhanging, we have to calculate P matrix. Otherwise, we can simply enter 0. In the given beam also, there is no overhanging, so we can simply enter 0. Since we are having only one coordinate, inside the P matrix also, we are having only one value, that is 0, because there is no overhanging in the given beam. In this formula, we have calculated the PL matrix and the P matrix. Only one is remaining, that is the stiffness matrix. Now let's see the size of the stiffness matrix. For 3 coordinates it will be 3 by 3. For 2 coordinates it will be 2 by 2. For 1 coordinate it will be 1 by 1. In this analysis we are having only one coordinate. So for 1 coordinate the size will be 1 by 1. Inside the matrix we will have only one value. Now let's see how to calculate stiffness. To calculate stiffness, first we have to apply unit displacement in every coordinate. In this analysis, we are having only one coordinate. Here we have to apply the unit displacement. Then we have to use the formulas. If the far end is fixed, the formula is 4EI upon L. If the far end is hinged, the formula is 2EI upon L. We have to be very careful. We have to apply the unit displacement in the restrained structure, not in the given beam. Now let us apply the unit displacement in the first coordinate, that is in the point B. In the point B, we are having a fixed support, but when we apply the unit displacement it is no longer a fixed support, it becomes a hinged support. Because in the fixed support there will be no displacement. Now let us see how to draw this curve. We are applying unit displacement in the point B. The point B is a joint. It is connecting two spans. So from the joint B, we have to make two clockwise curves, one towards the point A and one towards the point B. Now we have to check the direction of the curves. This curve indicates upwards. So the slope curve comes above the span. This curve indicates downwards. So the slope curve comes below the span. We have to give some gap between the fixed supports and the slope curve. You can see that I have given some gap between the fixed supports and the slope curve because in the fixed supports there will be no slope. Now let us calculate the stiffness. We are having only one coordinate, that is in the point B. So from the point B, we have to look on both the sides. First, let us look on the left side. On the left side, we are having a fixed support. If the parent is fixed, the formula is 4EI upon L. The length of AB is 5 meter. Let us apply that. Now let us look on the right of B. On the right of B also, we are having a fixed support. If the fair end is fixed, the formula is 4EI upon L. The length of BC is 5 meter. Let us apply that. After adding these two values, we are getting 1.6 EI. Finally, we have calculated the stiffness matrix. In the system displacement formula, we have calculated the K matrix, P matrix and the PL matrix. Let us apply the values. 1.6 EI inverse, we will get 1 upon 1.6 EI. 0 minus minus 26, we will get positive 26. Finally, we are getting the answer. We know that in this problem, the system displacement is the slope, which we got finally. The slope value will be according to the coordinate. In this analysis, the coordinate is in the point B, so we are getting theta B. In this analysis, we have calculated the unknown theta B. Now let us make the slope deflection equations and find the final moments. First, let us make the slope deflection equations in the span AB. We have already calculated the fixed end moments in the beginning. Let us apply them in both of the equations. In the point A, we are having fixed support. In the fixed support, there will be no slope. So let us cut theta A and make it as 0 in both of the equations. The length of AB is 5 meter. Let us apply in both of the equations. After applying the value of theta B in both of the equations, we are getting MAB and MBA. Now let us make the slope deflection equations in the span BC. In the point C, we are having fixed support. So theta C will be 0. Let us cut theta C and make it as 0 in both of the equations. The length of BC is 5 meter. Let us apply in both of the equations. After applying the value of theta B in both of the equations, we are getting MBC and MCB. In this analysis, we have calculated all of the moments. For MAB, we got a negative value because MAB is acting in the anticlockwise direction. For MBA, we got a positive value because MBA is acting in the clockwise direction. For MBC, we got a negative value. That means it is acting in the anticlockwise direction. Finally, for MCB, we got a positive value. That means it is acting in the clockwise direction. Now, let us calculate the reactions. First, let us take the span AB and calculate the reactions. In the span AB, there are two movements, MAB, which is acting in the anticlockwise direction, and MBA, which is acting in the clockwise direction. In the span AB, first I am going to find RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction, so it will be positive and the distance is 5. So 5 RA. The point load 50 kN is acting towards the point B in the anticlockwise direction, so it will be negative and the distance is 3 meter. So minus 50 into 3. Then there are two movements. The movement 29.5 is acting in the anticlockwise direction, so it will be negative. The movement 37 is acting in the clockwise direction, so it will be positive. After the calculations, we are getting RA is equal to 28.5 kN. To calculate RB1, let us apply the rule summation of vertical forces is equal to 0. In this span, there are three vertical forces RA, RB1 and the point load 50 kN. The reactions RA and RB1 are acting upwards, so both of them will be positive. 50 kN is acting downwards, so it will be negative. We have already calculated RA 28.5, so instead of RA, let us apply 28.5. In this way, we can calculate RB1, which is equal to 21.5 kN. Now, let us take the span BC and calculate the reactions. In the span BC, there are two movements, MBC, which is acting in the anticlockwise direction, and MCB, which is acting in the clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. The vertical reaction RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 5. So 5 RB2. The UDL 24 kN per meter is acting towards the point C in the anticlockwise direction, so it will be negative. When the UDL comes, we have to multiply with the distance and a distance upon 2. Here the distance is 5 meter, so 5 into 5 upon 2. Then there are two movements. The movement 37 is acting in the anticlockwise direction, so it will be negative. And the movement 56.5 is acting in the clockwise direction, so it will be positive. After the calculations, we are getting RB2 is equal to 56.1 kN. Now let us apply the rule summation of vertical forces is equal to 0. In this span, there are three forces RB2, RC and the UDL 24 kN per meter. RB2 and RC are acting in the upward direction, so both of them will be positive. The UDL is acting downwards, so it will be negative. For the UDL, we have to multiply with the distance to get the total load. We have already calculated RB2. Let us apply the value. In this way, we are getting RC is equal to 63.9 kN. We have calculated the reaction in the point B 2 times. Let us add both of the values RB1 and RB2. After adding, we are getting RB, which is equal to 77.6 kN. Now we are going to draw the shear force diagram. Before drawing, let us find the shear force values. I am going to calculate the shear force values from the point A and towards the point C. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the calculations here. Using the values, we can draw the shear force diagram. Now, we are going to draw the bending moment diagram. Before drawing the bending moment diagram, we have to make the free moment diagram and then the end moment diagram. Finally, we have to combine the free moment diagram and the end moment diagram to get the bending moment diagram. To draw the free moment diagram, we have to consider every span as a separate simply supported beam. First, let's see the span AB. In the span AB, there is a point load 50 kN. This point load is not acting on the center. If the point load is not acting on the center, the formula for the maximum bending moment in a simply supported beam is WAB upon L. Here W is 50, A is 2, B is 3 and L is 5. After applying the values inside the formula, we are getting 60 kN meter. If UDL is acting for the full span in a simply supported beam, the formula for the maximum bending moment in the center is WL square upon 8. Here W is 24, L is 5. Finally, we are getting 75 kN meter. We know that when the point load comes, the diagram will be in a triangular shape. When the UDL is acting, the diagram will be in a parabolic shape. Now let us see how to draw the end moment diagram. Using the end moments, we have to draw the end moment diagram. First, we have to draw this line. We have to draw these clockwise and anti-clockwise curves according to the moments. Then we have to see the direction of the arrows. All of the arrows indicate upwards. So all of the points come above the line. Even though in the joint B we are having two movements, we have to make only one point because both of these arrows are indicating upwards. That means we will have only one point. End moment diagram will be negative if it comes above this line. It will be positive if it comes below this line. Right now all of the points are coming above the line, so it is negative. Now let us combine the free moment diagram and the end moment diagram. You can see that I have combined both of the diagrams. Wherever they are acting alone without mingling with one another, we have to mark the values with the sign. Here the end moment diagram is coming alone. Here the free moment diagram, then end moment diagram, then free moment diagram, finally the end moment diagram. Wherever they are together, we are not marking anything. We just keep the space empty. Now we are going to end this session. Thank you for watching this video.